Yeah, ladies and gentlemen, let us discuss electromagnetism, a discussion on how it can be applied to make electric machines such as motors, generators, and transformers. Introduction. Electromagnetism is a very important topic for any nation intending to develop different technologies. Electromagnetism, though discovered in the 19th century, is a useful tool to date for manufacturing of electric motors, generators, and transformers. The main aim of this topic is to educate and motivate young African students, technicians, and engineers to learn electromagnetism, not only for the aim of passing exams, but for applying this important knowledge to be able to make our own machines and develop relevant technologies. Basic facts about magnets. On the 6th century, a suspended lodestone was found to point towards the same direction in Asia Minor. The direction they point towards are north and south direction. There is a slight difference between the magnetic north and geographic north. Magnetic materials are known as ferromagnetic materials. Cobalt, iron, and certain alloys are in the group of ferromagnetic materials. If you put iron fillings on top of magnet, you'll find many of the fillings or powder to be concentrated on north and south direction and forming a pattern representing a magnetic field. So figure 1 indicates a magnetic field around a magnet. So you can see that the fillings are concentrated on the north and south direction, and the lines of the magnetic field seem to be coming from the north pole to the south pole as shown in the figure. Magnetic effect of electric current. This was discovered by Oersted in 1820. It has been noted that if there is an electric current moving in a straight wire, it causes an electromagnetic field which is cylindrical or circular in shape around the electric wire. The corkscrew law states that the direction of lines of force surrounding an electric current is the same as the direction which a right-handed screw would have to be turned in order to move the screw in the direction of the current. So magnetic field on a straight conductor are shown in figure 2 and figure 3. Figure 3 shows the direction of magnetic field when the current is moving towards the paper. So it is depicted by a cross. So this is magnetic field around straight conductors with current moving towards the paper. So if you draw that will be represented by a direction where you will have to drive a screw in the direction of the current towards the paper. And the magnetic field seems to be moving from left to right, or it is, we can say, in a clockwise direction. And figure 3 shows the magnetic field around a straight conductor when the current is moving away from the paper towards the presenter. So the dot shows that the direction is towards the presenter, and the direction of the magnetic field is in anti-clockwise direction as shown. So figure 4 illustrates further the corkscrew rule. Here you can see on the right the screw is moving downwards. That is where the current is moving towards. And in order to move that screw downwards, you need to move the screw in a clockwise direction as shown. So these arrows, which are shown to be moving in a clockwise direction, represents the direction of the magnetic field around the conductor. And on the right hand, the screw is moving upwards. So in order to move the screw upwards, you need to move that screw in anti-clockwise direction. So that is the direction of the magnetic field. Figure 5 indicates the magnetic field around two parallel conductors, one moving towards the paper, the other moving outward of the paper. And you can see that the direction of magnetic field is as indicated in the paper, but in In between, you can see that the magnetic field becomes somehow flat due to the interaction between the two conductors. They are interacting against one another. One conductor with the current moving towards the paper, the other conductor with the current moving away from the paper towards the presenter. Effect of magnetic field around a solenoid. A solenoid is a wire making a spiral coil in approximate circular cross section and allowing electricity to pass to form electromagnetic field. The direction of magnetic field around the solenoid is similar to that of an ordinary magnet. If a piece of iron is placed within the solenoid, it strengthens tremendously the magnetic field. So you can see figure 6. It indicates the solenoid, a photo of a solenoid with the current. You can see the current is moving. Current may be moving from left to right. Then figure 7 indicates the direction of magnetic field around the solenoid, as you can see. Measurement of magnetic field. The magnetic field is measured by what is called as magnetic flux density, phi, which is B over A, where B is the strength of the magnetic field, A is the area on the area where the magnetic field is acting. So phi is magnetic flux density. So magnetic flux linkage is the total amount of magnetic field in all the coils. The units for flux linkage are in Weber turns, where phi is equal to magnetic flux density and N is the number of the turns. So magnetic flux linkage is phi times N, where N is the number of turns, phi is the magnetic flux density. Electromagnetic induction. If an electrical conductor is moved across a magnetic field, an electromagnetic force EMF is formed along the conductor. If the conductor forms a closed circuit, electricity will flow across the conductor. This effect is called electromagnetic induction and was investigated by Faraday. Fleming's right-hand rule. If a current flows in a right angle direction to magnetic field, both the field and the current will cause a force perpendicular to both of them, having a magnitude F is equal to BL times I, where F is the magnetic force, B is magnetic field strength in Webers per square meter, L is the active length of the current flow, that is in leg of the wire, and I is the current in amperes. Application of electromagnetic forces, electric motors. Rotational movements are important in different parts of industry, such as conveyor belts, drilling machines, lathe machines, water pumps, and hence electric motors are very important machines in any society. Motors are necessary when we need to turn electrical to mechanical energy. Electric motors are based on the principle that if you pass electric current to an electric coil, which is surrounded by magnetic field, it will result into forces which result into relative movements between the electric coil and magnets. These relative movements, if well arranged, cause rotations. So important parts of electric motors. Rotor. This is the moving part of the motor which rotates the shaft. Stator, the stationary part of the motor. It can be made of permanent winding or magnet. And then we've got bearings. We support the rotor and are supported by housings. In some motors, the electric parts are made to rotate while the magnets are made to be stationary. In other motors, the electric parts are made as stators, while the magnetic parts are made as rotors or rotating parts. A discussion of rotor and stator arrangement. However, making the magnetic part to be a rotor to be as a rotor or to be rotating, while the electric part is stationary, has the advantage of keeping the electric coil stationary, which is easier to avoid loss of contact. Otherwise, making electric conductors to rotate may cause loss of contact or may need extra efforts to maintain the contacts during rotation. So that is the photo of an electric motor. Faraday's law. An electromotive force is induced in a circuit when the magnetic flux linkage the circuit changes. The value of electromotive force is directly proportional to the rate of change of flux linkage. E is equal to phi times N over T. Phi times N is the magnetic flux linkage and T is the time. So E is the electromotive force as in volts. Calculation of electromotive force. When an electric conductor moves across a magnetic field, E is equal to B times L times V, where E is the electromotive force in volts, B is magnetic field strength in Webers per square meter, L is active length of the current flow, e.g. length of the wire, V is the velocity of the conductor perpendicular to the flux in meters per second. Electric generator. Electric generators are opposite of motors. These are used to transform mechanical energy rotation into electricity. These work on a fact that when there is a rotation of an electric conductor with respect to a magnetic field, or when there is a rotation of magnetic field with respect to an electric conductor, the electricity will flow in the conductor if there is a closed circuit. The most efficient type of generator is when the rotation is in the magnet and the electric conductor is stationary. The main parts of generators are engines, alternators, and control panels. Alternators have the main parts which are stators and rotors. Most rotors consist of magnets which rotates around stators. In which case, the stationary part on the alternator is the electric conductor. Electric generators are used to convert electromagnetic forces into electricity. Generators for alternating EMF are usually called AC generators or alternators. It is particularly convenient to keep conductors stationary and to allow for connected magnetic field to rotate to avoid slips in the electric connections. So that is the figure of electric generators. You can see figure 9, and you can see the north and the south pole and the conductors, conductors rotating in between. So you can see when the YY is in adjacent to the northern pole and south poles, and when the on the x direction, the conductors are perpendicular to the north and south poles. Transformer. Electricity is generated in electric powerhouses. Because it has been noted that during transportation of electricity in wires, when the voltage of electricity is high, the losses in electrical energy are smaller compared to when the voltage is lower. When electricity reaches the destination substations, it is important to lower the voltage because the high voltage is dangerous to human beings and the appliances, hence the importance to lower the voltage. The power may remain the same, but the voltage vary with currents. Transformers are electric appliances applying electromagnetism to raise or to lower the voltages of electricity. During transportation of electricity for long distances, it is important to raise the voltages in order to avoid electric losses. The transportation of electricity at lower voltages cause higher electric losses. The transformer basically consists of a magnet having two sides connected to electric coils. The side having bigger number of coil windings results in higher voltage than the side having lower number of coil windings. You can see figure 10 shows the diagram of a transformer. You can see the transformer is got a big magnet with the electric windings wire which are fixed in coils. On the left side of the transformer, you have got that the wires are in red color and the coils are closely spaced, and this is normally used on the side where the voltage is supposed to be higher. On the right hand side, you have got the blue coil of wires which have got wires which are spaced at bigger distances, and this is where you want the voltage of that side to be lower. So we've got the primary side and the secondary side. The primary side have got red wires which are closely spaced, and the secondary side have got blue wires which are spaced at higher distances. The power of electricity is given by the formula P is equal to volt times current is V times I. So the power is constant. You've got the primary voltage times the primary current is equal to secondary voltage times secondary current, and it is equal to power. So the power is constant. So Vp is the primary voltage, Ip is the primary current. From the diagram, a primary side of the transformer has higher voltage, and the secondary part of the transformer to the consumer has lower voltage. The power of electricity is given by the formula. You have got Vs is equal to secondary voltage, Is is the secondary current. From the diagram, the primary side of this transformer has higher voltage, and the secondary part of the transformer to the consumer has got lower voltage. So you have this formula that primary voltage times the primary current is equal to power is equal to secondary voltage times the secondary current. So if you rearrange that formula, you'll have got the Vp over Vs, or the primary voltage over the secondary voltage is equal to primary current, or secondary current divided by primary current is equal to number of windings on the primary side divided by number of windings on the secondary side. So that is a challenge to the African intellectuals. I have talked about the transformer, I've talked about generators, and I've talked about motors. Now the question is, can we make manage to make our own motors, generators, and transformers? The second question is, what is hindering us from making development of these important components? The third question is, what do we need to do to acquire these technologies? And the fourth question is, for students studying engineering and sciences, what motivation are you receiving to provide solution to your own continent? Ladies and gentlemen, thank you for listening to me.